July 1st, 2025, a new blip on astronomers' screens. At first, Comet 3I Atlas looked routine. Then came the signal, strange, unmistakable, and from far beyond our solar system. Harvard's Avi Loeb issued a stunning public claim, setting off a global scientific scramble. But buried in the data are anomalies neither NASA nor anyone watching can explain. Why are the world's top experts suddenly on red alert over an interstellar visitor? And what could we be missing? Avi Loeb's words landed like a thunderclap. On October 27, 2025, during a live interview on Fox 32 Chicago, the Harvard astrophysicist did not hold back. With 3I Atlas nearing its closest approach to the Sun, Loeb called on the global science community to treat this as a once-in-a-generation opportunity. He argued that if there were ever a moment for an interstellar object to reveal something truly unexpected, maybe even a sign of alien technology, this was it. He pressed for immediate data release, criticizing delays caused by the ongoing government shutdown, and pointed to key dates: satellite images acquired on October 2nd, perihelion on October 29th, and a close Earth pass coming in December. The impact was immediate. Science newsrooms scrambled to cover the story, and NASA's 3I Atlas explainer page recorded its highest web traffic since launch. Social media erupted. On X, hashtag 3I Atlas and hashtag Avi Loeb surged, driving a five-fold spike in posts and replies within a single day. Clips from the interview spread across YouTube, racking up over 6 million views in 48 hours. Public telescope portals and data archives saw user numbers triple as amateur astronomers and the curious raced to access real-time tracking data and archived images tagged to 3I Atlas. Loeb's statement poured fuel on an already smoldering debate. Mainstream planetary scientists urged caution, emphasizing the need for hard evidence over speculation. But the urgency was undeniable. In the space of 48 hours, a single interview had pulled the science community and the public into a high-stakes hunt for answers, turning 3I Atlas from a technical curiosity into a headline-grabbing mystery. When astronomers first spotted 3I Atlas on July 1st, 2025, the object's hyperbolic trajectory stood out immediately. This path, open and unbound, confirmed it was not from our solar system. Just the third time in history such a visitor has been confirmed. The Atlas Discovery team in Chile, already known for their rapid response to potential impact threats, quickly realized this was something different. Their automated system flagged the object's speed and brightness as outliers, and within hours, orbit analysts at NASA Jet Propulsion Laboratory verified its interstellar status. Compared to its predecessors, 3I Atlas is in a league of its own. Oumuamua, detected in 2017, was cigar-shaped, less than a kilometer long, and so faint that even the world's largest telescope struggled to track it as it sped away. 2 years later, 2E Borisov arrived, a true comet with a bright active tail and a nucleus estimated at about half a kilometer across. But 3I Atlas appears larger and more enigmatic. Early brightness estimates put its apparent magnitude near 9.8, making it accessible to advanced amateur telescopes. Its nucleus is believed to be up to several kilometers wide, potentially rivaling the size of Manhattan. That is several times the mass of Borisov, and a far cry from the slender, tumbling shape of Oumuamua. For the Atlas team, the discovery was both a technical triumph and a scientific puzzle. Their prompt coordination with global observatories ensured that 3I Atlas would be tracked from every possible angle. The object's sheer size, speed, and brightness set a new baseline for what interstellar visitors can look like. These numbers gave astronomers a clear, quantitative foundation, one that would soon make the anomalies in Atlas's behavior impossible to ignore. A sudden surge in brightness set off alarms across the astronomical community. Early November brought a series of observations that did not fit any standard playbook. On November 8th, veteran comet photographer Michael Jaeger captured time-lapse images, revealing a compact halo enveloping 3I Atlas and a faint, sunward-pointing jet. Those are features that should not be so subdued in an object of this size and speed. The usual expectation for a comet this active is a sprawling luminous tail and a fluffy coma, but here the visual profile was almost contradictory. a nucleus brighter than Borisov, yet surrounded by a halo so tight it looked artificial in comparison. Meanwhile, ground-based teams worked around the clock. The MeerKAT observatory, known for its sensitive spectrographs, detected distinct absorption lines in the optical range, evidence of hydroxyl radicals breaking free from water molecules as sunlight hit the icy surface. These lines, usually a telltale sign of vigorous outgassing, appeared at unexpected strengths, hinting at hidden reserves of volatile material or unfamiliar chemistry at work. Even as the object brightened by nearly a full magnitude over just a few nights, the classic cometary tail remained stubbornly faint. In side-by-side images, the difference between 3I Atlas and a typical solar system comet was stark. Where a normal comet would glow with a sprawling, fan-shaped tail, Atlas presented a concentrated, almost star-like core with only the thinnest veil of dust. The presence of sunward jets, material streaming toward the sun, not away, added another layer of mystery, challenging long-held assumptions about how cometary activity should behave. Each new dataset sharpened the sense that this was no ordinary interstellar traveler, demanding a coordinated, multi-instrument campaign to decode its secrets. NASA's Jet Propulsion Laboratory faced a growing puzzle as 3I Atlas rounded the Sun. The object's trajectory, mapped in detail by JPL orbit analysts, began to drift in a way that gravity alone could not explain. Numbers from the tracking stations showed a persistent, measurable acceleration, small but undeniable, acting on the object as it sped away from perihelion. Calculations pointed to a force equivalent to several meters per second, gained over just a few weeks, a change that should have required hundreds of kilograms of mass to be ejected every second if the culprit was outgassing. Yet the expected debris was missing. In theory, a comet shedding that much material would leave behind a spectacular display, a sprawling bright tail, and a coma stretching for thousands of kilometers. Instead, images from ground-based telescopes and Mars orbiters showed a nucleus surrounded by only the faintest halo, with little evidence of the chaos that such mass loss would create. The usual markers of violent outgassing, broad jets, clouds of dust, and a roaring tail, were barely present. Spectroscopic data from MeerKAT and the Swift Observatory revealed a low water signature, with hydroxyl radicals detected at levels far below those seen in typical comets of this size and speed. JPL technical teams ran through every scenario. If the acceleration was real and not an artifact of measurement, the physics demanded a source of momentum. The numbers did not add up. Too much push, not enough visible debris. Polarimetric studies hinted at unusual surface properties, but nothing conclusive. Each new dataset brought sharper focus to the core anomaly, driving the need for higher resolution imaging and deeper analysis. The scientific tension was now front and center, a quantitative conflict between theory and observation that refused to resolve itself with the tools and data at hand. Debate over 3I Atlas now stretches far beyond academic circles. On one side, planetary scientists call for patience, insisting that only high-quality data can settle questions about the comet's origin and behavior. On the other, a growing network of citizen astronomers is rallying online, determined to keep the search transparent and public. The Virtual Telescope project, led by Gianluca Massi, has become a digital gathering point, streaming live feeds as 3I Atlas climbs higher in the pre-dawn sky. The most recent broadcast drew 70,000 concurrent viewers, an all-time record for the project, while chat moderators struggled to keep up with questions about jets, brightness, and rumors of hidden signals. Institutional networks are responding in real time. The International Asteroid Warning Network issues bulletins as new positional data arrives, and global observatories race to secure time on flagship telescopes. The James Webb Space Telescope and the European Space Agency's JUICE probe both have observation windows scheduled in the coming weeks, with the James Webb Space Telescope aiming for high-resolution spectra and JUICE hoping to catch the comet as it sweeps past Jupiter's orbit. Meanwhile, a Juno mission proposal to pivot its camera for a brief Atlas flyby is under review, adding to the sense of urgency. Amid the rush, some voices warn against hype. Speculation about unreleased high-rise images spreads on forums, yet official mission logs show no evidence of hidden data. Instead, the focus is shifting to the next wave of observations: high-cadence spectra, coordinated amateur campaigns, and open-source data sharing. For now, the countdown is on. Every new dataset could tip the scales, and the public, amateurs and professionals alike, are watching, ready to catch the next big clue as it arrives. Right now, astronomers race to decode the data streaming in. Each new interstellar object forces us to rethink what is possible and what we might be missing. Cosmos is not silent. What we choose to hear next could redefine our place in it.